basically today's job. It will go from the Lagrangian to the Hamiltonian. This is something which is very familiar to all of you, at least for the non-singular case. And I will start describing this with the non-singular case slightly differently than usual, simply because I will kind of sort of use that as a warm-up exercise. So as you all know, our Lagrangians are functions of q dot and possibly time, but we are not going to worry too much about the time. The Hamiltonian, oh, you're here. Sorry, I thought today you were too busy with some thing or that. Okay. So I was just talking about the passage from Lagrangian to the Hamiltonian. So our L is a function of q and q dot, and as you again stuff everybody knows, del L del q dot I gives you the Hamiltonian momentum, and these momenta come out as functions of q dot. And in the non-singular case, what you have is del p I del qj dot, this wij, the same Hessian that we met at the very beginning. If the determinant of this w is not equal to 0, this is a non-singular case, then we should be able to solve, at least locally, for the velocities in terms of the momentum. Neither of these work? Oh, there's some switch here. A screen. Let's switch on whatever. और कुछ ऑन ही तो है ना स्क्रीन का ये वाला स्क्रीन कंट्रोल क्या अच्छा काम कर रहा है okay and now this means that I should be able to write q dot I as some function of q and p. Now this is what is going to fail, at least this is not something we are going to get always when we have a singular system, at least not for all the velocities, but for the time being we are dealing with a non-singular system where all the q's can be rewritten in terms of the position and momenta variables, and we have this famous Jacobi function which is basically pi qi dot minus L, again functions of q and q dot. Remember here the pi's are functions of q and q dot. So this whole expression is a function of q and q dot. And even before we get to the Hamiltonian, this is a thing of interest because at least for Lagrangians which are time independent, this thing is a conserved quantity that you all know. But the Hamiltonian H is actually what you get when you do this. So replace the qi dots by these functions of q and p, and in the L, for each of the q dots you actually replace them by f, right? Or if you want to write this collectively, by all the fi's, all the qi's of course, and all the qi dots gets replaced by all the fi's. Okay? Now I am going to derive the Hamilton's canonical equations here in a slightly different way than the usual ones that are carried out in most textbooks. It's slightly more involved way, but also this will be a good warm-up for what we need to do later. So let's say if this is a Hamiltonian expression, this is a full functional expression in terms of functions of q and p, right? The fi's here are functions of q and p. Here all the q dots have been replaced by fi, which are also functions of q and p. So if I want to do a partial derivative with respect to qi, how should I proceed? The pi's are independent of q's, so no derivatives here. This is a constant as far as this derivative is concerned. But the fi has to be partially differentiated with respect to qi. Okay, so I should not really call it I, let's say pj del fj del qi. Of course, this was a dummy index of summation. I have to change that and change that because I am talking about specific qi here. And what about L? When I differentiate L with respect to qi, what will I get? I will get actually two terms. One, from the fact that the qi's are there already, and then you have minus del L del Qi, and just to get into a good habit, let me remind ourselves that all the Q dots have been replaced by F here, right? That's the standard partial derivative that you do. Then you have another term which comes in because all these Q dots have been replaced by F's, which are actually functions of Q and P. So Q is also very much in here. So del L del Q dot J, the jth velocity, I am differentiating that with respect to. Again, remembering that after you do the derivative, you actually put all the Q dots equal to F times del Fj del Qi. This, of course, is standard partial derivative of a function or a function. Okay? And now, notice that this thing, Pj and del L del Q dot J, after you replace the Q dots by F, are exactly the same thing, right? So this term cancels out this term, and you left with del H del Qi is actually what you get when you calculate minus del L del Q dot Qi, and then put Q dot equal to F. So this is what explicitly differentiating this Hamiltonian function with respect to Q gives you. But then this should be pretty familiar, because Lagrange's equation of motion has already told me that what is this quantity? This is ddt of del L del Qi dot, and del L del Qi dot is my Pi. So this is minus Pi dot. Of course, a very familiar equation. Pi dot is minus del H del Qi. We are getting this not by starting from the differential of the Lagrangian and doing some tricks. We are just explicitly differentiating whatever we have. And again, why am I doing it this long way? Because soon for singular Lagrangians, this is essentially what you have to do in a slightly more complicated situation. Okay, so having done that, that's your del H del Qi. And what about your momentum derivative, del H del Pi? Now, that was your H. So you differentiate with respect to Pi. The first thing that will happen, this is really Pj Fj. So when you differentiate Pj Fj with respect to Pi, you are going to get a delta Ij times Fi. That will of course give you Fj, that will give you Fi directly. But that's not the only term, right? Fi also has P's in it. So you will also have to do Pj del Fj del Pi. And then in the Lagrangian itself, the original Lagrangian of course was a function of Q and Q dot. But the Lagrangian which is sitting there is not really the original function L. Here all the Q dots have been replaced by F's. So the F's have the P's in them. So minus del L del Q dot J, all the Q dot vectors set equal to F, del Fj del Pi. And once again you should see that these two terms just cancel each other out, right? This is Pj and that's del L del Q dot J. So they're exactly the same thing. So they cancel each other out and you're left with equal to Fi, and Fi of course is nothing but Q dot I. Okay, one important point which is really rather trivial at this stage but it's important to bear in mind is that to get to del H del Pi equal to Q I dot, you did not really have to use the Euler-Lagrange equations of motion, right? Fi by definition were Qi dots, whereas on the other hand, del H del Qi worked out to be minus del L del Qi dot. There, after we use the equation of motion, we end up with minus Pi dot equal to this. Okay, so this is just a different way of finding out the standard equations, because this is still the standard system, the non-singular system. Now, in a singular system, things are more complicated. So let's start with a slightly simple situation. So our Lagrangian, the one we will start out with, will be a special case which is also quite common. It's one of the most common special cases where the Lagrangian is a quadratic in velocities at most. Okay? That's the most common situation. And so the general case can be written down, not the general case, but this special case can be written down like this. So It could have a quadratic piece, a linear piece, and a piece which does not have any velocity in it, and that piece typically is what you would call the potential. It doesn't have to be the potential energy, it's just something which you identify with the potential energy usually. So this is a very general, but not completely general form, right? You could have non-quadratic Hamiltonians as well, where velocity is not quadratic, but this is pretty common. And one very important trick which I'm sure many of you already know is when you form this q dot del L del q dot term, this sum, you are differentiating a function with respect to a variable and multiplying that variable and adding them together. Now, there is a very special result in mathematics which is called the Euler theorem for homogeneous functions, which tells you that if you did this with a homogeneous function, the function just gets multiplied by the degree. So, when you do this to this term, this actually becomes twice t, twice itself. This becomes the same thing as itself, and this thing vanishes, right? Of course, there is no q dot here anyway. So, this term is actually double of this plus this, and when you subtract the Lagrangian from that, what happens is this piece cancels out, and you are left with this plus that, right? In fact, that's essentially why for purely quadratic kinetic energy terms, which is very common, your Hamiltonian works out with kinetic energy plus potential energy always. But actually it's not, actually kinetic energy would usually have terms like this as well, and also a term which is independent of q dots perhaps, especially if you are going to say a different say you are changing your coordinate system or you have a movable origin, that kind of thing. Then you would end up with an additional piece here which is part of the kinetic energy also. So, it is only the quadratic part of the kinetic energy plus the potential energy which usually comes out, okay, and minus the term which is actually independent of velocity. Anyway, so that is an easy way to work things out. So, but before we get there, first let us go through the PIs. The PIs are in this case simply these Wij's are of course taken to be symmetric in I and j. Any antisymmetric part would contribute nothing because it is being contracted with q dot I, q dot j. So, because of the symmetry, this simply gives you this. And this is a function of q. Okay. Now, here it's obvious there is a Wij's where form the matrix which is invertible. You can directly write out q dot in terms of p's and p's directly and the q's because eta I q's also and w also has q's in. Okay. However, if Wij is singular, which is our case, so if rank of w is less than the number of degrees of freedom, the number of variables here. Actually, 2n is the number of phase space variables, but the number of p's here is n. If this happens, then what you have is there are n minus rw null eigenvectors, just the same kind that we saw before of this function of this matrix W. That is, you have V's. So, there are multiple V's, as many as n minus rw. So, each of them is labeled by an alpha, and the components I can just write as I. So, this gives you this thing, right? So, Vi alpha eta I, right? And Vi alphas are eigen, so Vi alphas are basically solutions of this. So, Vi alpha q depends on q of course, because W's do. So, this is basically the eigenvector, null eigenvector definition. Vi's are the null eigenvectors. And now, this obviously gives you constraints between p's and q's. P's and q's are no longer independent, right? And in particular, because Rw is a finite number, some finite rank, you would be able to get Rw independent p's from here, and there will be others, the n minus Rw, which will not be independent. So, let us just Okay, here it's a matter of notation. I've been using I, J, K, these letters from the middle of the alphabet for variables which run all the way from 1 to n. Okay. Just for convenience, we are going to say, if I write something with a suffix ABC, something near the beginning of the alphabet, these are the ones which are the independent ones. So A will basically run from 1, 2 up to RW. Okay. And again, just for convenience, we are going to use Greek letters to indicate the ones which are constrained, which are still constrained, which will not be independent. So, and beta typically go from RW plus 1 to n. All the Greek indices ones are the constrained ones. So, this is just for notation, it makes life a little bit easier later on. So, now this equation that we have written can be broken up into two pieces, one with only the constrained ones, that is these betas, and the others only with the i's, with the a's, the non-constrained ones. And I can write this as something like this. V beta, the beta-ith component for the alpha-ith vector, P beta, is V I alpha eta I. These are of course functions of Q. So, of course, is this minus V A alpha P A, right? I have just taken the ones which are independent, these P's on the other side. So, these are the constrained ones. So, what the equations they obey essentially go like this, where M alpha beta is nothing but the matrix made out of these Vi components. So, the beta-ith component of the alpha-ith null eigenvector, that is what my M alpha beta is. And that of course depends on Q. And on this side, you have something which depends on what? Depends on Q's, of course, because both these and these depend on Q's, but it also depends on momenta. But not all the momenta, only the independent ones, only the PAs. So, at least in this case, we see that, okay, and what about these M alpha betas? Can we invert them? Can we invert this matrix? If we can, then of course the P betas can be written down directly in terms of as functions of Q and P's, right? The question is, can we invert M alpha beta? And the answer is we can. And the reason for that is simple. Suppose the M alpha betas were not invertible. If they were not invertible, it would have a null eigenvector, at least one. And using that you can immediately show that there will be a connection between. So, if you hit with a null eigenvector of this side will vanish. So, you will get a connection involving Q's and PAs, which means PAs will no longer be independent, which is a contradiction, of course, right? So, basically, the P betas should be something you can calculate using this. So, M inverse being an inverse of a matrix which depends only on Q will also depend on Q in general. F alphas depend on Q and P alphas. So, this is going to be some function G beta of Q and the unconstrained momenta, independent momenta. So, basically, at this stage we have not really used the equations of motion or anything. We have just looked at the definitions of P, right? I have just taken L, differentiated that with respect to Q dots, found out what the P's are, and we have found those P's, some of those P's will obey constraints. Okay? And the constraints we will write, so these are called primary constraints in Dirac's language. So, phi beta, which is by definition P beta minus this G beta, Q and P alpha, okay, must be 0. Note that there is no equation of motion being used here. These are 0 by definition, from the definition of the momentum, okay, right? So, for the case of singular Lagrangians, the moment you calculate the momenta directly, you will find the sum of the momenta will come out to be constrained. And there will obey some relation like p beta minus some function of the other momenta and the q's equals 0. The simple example that we started out with, let me just remind you of that one, which we have seen over and over again. We have done this twice, one with a plus, again with a minus. There the constraint was an obvious one. You just calculate px and py from here. Px works out to be x dot plus y. It depends on position and velocity. But py turns out to be 0, which is of course a constraint. There the function g alpha is very simple, the function is just 0. Okay? So this was a particularly simple example, but it could have more complicated connections between the p's. Okay? But you will always get primary constraints, and the thing to note is these constraints don't depend on equations of motion or anything. They come directly from the definition of how the momenta arrived at from the Lagrangian. Okay? Now there's only one. Yeah.
Equation above is already these constant equations, right?
Yeah, this is the constraint equation.
The top line. D alpha,
Yeah. That is the constraint equation. I've just rewritten that in this form. So when I write it in this form, these phi betas are what we are going to use, where p betas are expressed as some function of q's and the rest. The constraint equation is the one right on the top, but you can rewrite them in this form. And these are the phi betas we are going to actually call, we are going to use them directly in the process later on.
Will m always be invertible?
Because if m were not invertible in this case, you are saying can m be inverted, right?
I mean, always.
Yeah, because if m were not invertible, remember we know that there are PA independent momenta because rank is RW. There are that many independent momenta there, right? And Q's of course are anyway independent. I'm only worried about the Q dot relationship here. Now, if on the other hand, let me just repeat, if this was not invertible, it would have its own null eigenvector. If you hit it with that on both sides, you'll get this side vanishing. You'll get that null eigenvector times f alpha contracted, gives you some relationship between Q and P's. The PAs, which of course can't be there. Then the PAs would not be independent. Right? Okay, so the only, catch about this argument is that here we have actually only used specifically a special kind of Lagrangian. A very common kind, the kind that we deal with most often, but not the most general kind. However, something like very similar can also be done for the more general kind. It's just a bit more abstract.
Small nitpick, A inverse beta alpha.
Yeah, right. Yeah, and it's not necessarily symmetric. Right, you're right. You're perfectly right. That's important. That's not really going to be very important for the rest because we are not really going to explicitly use this all the time, but that's an important point. And M is not guaranteed to be invertible. Like W was, symmetric. W was symmetric, so for that we didn't really care, but here we should. Okay, now coming to this next point, suppose we did it for a general thing. Suppose we just started with this definition, and then the fact that det W turned out to be 0 for a singular system signaled that we will not be able to find all the Q dots independently. But what we should be able to do is this. Okay, let me just put it this way. Okay, what is the largest submatrix of W which will be invertible? What is the size of that? That's the rank, right? That's another way of looking at the rank. And in fact, by doing the so-called row elimination or whatever process you use, you can always ensure the first RW rows are going to be non-zero and the rest are going to be 0 at the end, right? And then if you need to, you can relabel the indices and ensure that WAB, this matrix where A and B run from 1 to RW, is the largest invertible submatrix. The only thing you may have to do is change the label somewhat. Maybe the 15th one has to be brought to the beginning or something. So if you have just done this in linear algebra, it will be very easy to understand what we are doing here. Okay? Now if that happens, what is guaranteed is this. So, for one through RW, you should be able to solve all the q dots, but then, so a q dot will be a function of a function fa of the q's, and again what else? Remember the p's, the equations would look somewhat like this. You have rows like this with the p's sitting here in the end, and ultimately the other p's, the p's below RW rows, they have all ultimately become 0 by the elimination process. This entire row has become 0. Of course, what is guaranteed is that these rows become 0. If this one also doesn't become 0, you end up with an inconsistent set of equations. We are assuming that we have a consistent set of equations, so these other p's have somehow cancelled among each other. So you are just left with the first a p's and their first RW p's, and there are some linear combinations of them here. You have all the, but here you have n columns, one column left, and here you have the q dots, that is variations of the q dots you would really want to be, changes of q dots by a small amount, because we are really looking at the Jacobian here. So these q dots can all be written down in terms of these p's and these q dots, right? Because after all, this part is invertible, but you also have these many q dots sitting here. So ultimately the equation really becomes this matrix acting on these q dots is equal to these p's minus whatever combination of these other q dots. So q dots which run beyond this RW plus 1 through to n, they will also be there in the answer. So this will be q, a function of q's, the PA's, and q dot betas. Remember, our notation is A runs from 1 to RW and beta runs from RW plus 1 to n. So those ones which you could not eliminate. Okay? So this is a very generic scenario. This is what will always happen. Okay? And now, if you go back to the PI equation, the PI equation started out being some function h, I am calling it h now, not f, because I will reserve f for later. This f is, f is already here. The PI are the original PIs, so they are written in functions of q and q dots. Okay? But among the q dots, the first a of them can be replaced by these functions. So you can write hi of q fa, and then the other q dots will stay on. So this is the kind of functional form that you are going to get for the PIs. All I have done is just taken these solutions, plug them back in the PI expressions. Now you see, these are expressions for all I, right? But for the first RWIs, the A's, you have PA on this side. On that side you have Q's, functions of Q's and P's, and Q dots. But the first PA's are actually independent, right? First RWPA's, they are the independent ones. So for them, this equation has to actually just reduce to, after you do everything, it just has to become PA equal to PA. Okay? Has to be, because if that didn't happen, then the PA's would be related to the other things. But what about the case for P alphas, that is for the indices which go beyond RW, the constrained ones? Now you will get a function which will have Q, the FA's, and apparently the Q dot B's also. But if you had the Q dot B's left in that expression after you did all this, then you should be able to at least solve one of the Q dot B's, betas, in terms of all the momenta and positions, which of course you can't. That's why you have already said that these are the ones you can't solve for them at all. So this function will have to ultimately become a function of only Q and the PA's. Remember, here through the F's, they have Q's, F's have Q's in them, P's in them, Q dots in them, all Q dot betas in them. But ultimately, all these Q dot betas have to cancel out among each other, Because if you had a q dot left here, you should be able to solve for that. At least one of them, if not all of them. And that would mean you end up with more independent q dots than you actually can have. Okay? So this slightly abstract reasoning ultimately tells us that even in the most general case, not for the, that is most general singular Lagrangian, you will ultimately have a situation like this, that unlike our non-singular case where all the q's or all the q dots could be written down in terms of functions of q's and p's, here only the first RW q dots can be written down that way, functions of q's, then all the PA's and all the q dot betas, right? These are for the q dot A's. And all the P betas or P alphas, whatever you want to call them, they can be written down as functions of G alpha, Q and PA. That will happen in general. We saw that explicitly for the case of quadratic Lagrangians, where it was easy to sort of work everything out, but even in the general case, this is bound to happen. So here A's, let me remind you once again, A, B, these indices run from 1 to, okay, I should not really write PA here, that might sort of confuse people into thinking that has to be the same index. Q dot A, all the PBs, so AB will run from 1 to RW, and alpha, beta, etc., these will run from RW plus 1 to N. So independent constraint, right? Now the reason why this is going to be important is now let's look at the canonical Hamiltonian, the pi qi dot minus L, and now clearly see what I can do about it. So we will call this H0, which by definition is HC restricted to the part of phase space where all these constraint equations, these phi alpha, p alpha equal to g alpha q p alpha, which we are going to call phi alpha equals 0. That is by moving, so phi alphas are simply a rewrite of this. Phi alpha by definition are these functions p alpha minus g alpha qpa. Unfortunately, or actually not really unfortunately, but you have to keep track of which are the dependent variables or which are the independent variables here. Once you keep track of that properly, the rest of the calculation is really not that difficult. But the only real problem is keeping track of exactly which are the variables that we are actually taking to be independent. So these constraints, which are n minus Rw in number, the primary constraints, essentially tell you that you cannot have motion in the entire phase space. The 2n dimensional phase space is not available to you. Every constraint you put in reduces dimensionality. In fact, because you have n minus Rw constraints, the dimensionality of the phase space is 2n minus n minus R plus Rw, that is n plus Rw, right? At this stage, no equations of motion have come in. It's just that by definition of the momenta, you have ended up with a situation that you don't have this 2n dimensional phase space available to you. You only have an n plus Rw dimensional subspace available, which we are going to call our constraint subspace gamma p. This is p reminds you of the phase and gamma for all the constraints taken together. Okay? And this is going to be what? Well, you had pi qi dot. Now let's split that in two pieces. And here again, I'm not going to write the summation sign. I'm going to assume that you know that A runs only over 1 to Rw. And betas, etc., alpha betas run from Rw plus 1 through on. So Pa multiplied by q dot A. But when you actually do the Hamiltonian, what you do? You change all the q dots. You try to change all the q dots to p's. But here you can't change all the q dots to p's. You can only change the first A of them. So PAFA is fine. But unfortunately, you will have to have terms with the q dot betas. But q dot betas gets multiplied by g betas, where g betas actually depend on q and PA. Right? These are the p betas. But they we know have to obey this equation. Followed by a Lagrangian where you had q and q dot as an argument. Now I want to change the q dots as much as possible as functions of q and p. But for that, we can do it only for the first a q dots I can change in terms of functions of q's and p's. The others, okay, so this is my so-called canonical Hamiltonian restricted to our constraint space. Okay. The restriction of course comes in because I am putting in, instead of p betas I am putting in the g betas and so on. But now this looks like a pretty nasty thing because you have all the q dot betas which you can't get rid of, right? You would want a function of q's and p's, right? Now that all the p's are not independent, if you had it only in terms of q's and independent p's, that would still be nice. But here, the q dot betas are apparently still inside this expression. But notice that if we want to find out what del h0 del q dot beta is, of course, when I say del h0 del q dot beta, I mean differentiate holding q's and the other p's, the independent p's, the PA's constant. So what will happen here? When I do this differentiation, will I get anything from here? Actually, I will. Remember, what does the FA depend upon? That's why this is important to remember. FA depends on the q dots. PA's don't. So PA del FA del q dot beta. Okay? What about this? G beta q dot beta of course gives you G beta. G betas, all the G's, they don't have any q dots in them, right? So G beta does not get differentiated. What about L? Where are the q dots in L? Q's of course have no q dots in them, but the F's have q dots in them, and among all the n q dots, the last n minus RW1s are actually still there, right? So there will be two kinds of derivatives. One will come from del q dot A, and there you have to put q dot. Okay, I don't really want to complicate notation too much, but I am putting a tilde below to remind you that you are not going to change all the q dots to f's. You can only change the first RW of them to f's. Okay? Del FA del q dot beta, right? That's just chain rule. But there will also be del L del q dot beta explicitly, because the betath q is also there as an argument. And this is again with the same change. All the q dots, at least the first RW q dots, have to be changed to F. So it looks. Which one? Sorry.
Second last one.
You mean this term?
No, the one before that. Yeah.
Here, this one. So del L del q dot A. So there's the eighth q dot, which actually has been replaced by FA here. So L actually is a function of q dot. So when you differentiate it, you are looking at the second argument of the second set. That's del L del q dot A. After you do the partial derivative, you put in q dot A equal to FA. Okay, this is a slightly more cumbersome way of writing it, but this is an explicit way of keeping track of exactly where all the variables are going. So it looks like a very nasty thing, but now note this is G beta, right? That's actually P beta by definition. What's this? Del L del q dot beta. After you put in q dot tilde equal to F. That's exactly the same as G beta, right? What about this? Del FA del q dot beta is there in both terms, and the thing multiplying it, contracting with that actually, is PA here, del L q dot A here. Again, after that you are going to do the substitution, but that also is exactly the same as this. So one result that actually you saw in an example we worked out just as a sort of temporary thing long ago. If you try to calculate the canonical Hamiltonian, then at least those pesky velocities which did not really should not really be there, but apparently are there, actually are not there any longer. It's always, this thing is always 0. So the H0, the thing that you get by starting with the canonical Hamiltonian and imposing the constraint, somehow ends up getting rid of all the q dots. Okay. We saw that in one example, looked like a bit of an accident there, but that's not an accident. Let me just remind you of that example at least. Again, our favorite and maybe by now pretty boring example. Let's start with this one. When you went to H0, that is the canonical, wrote down the canonical Hamiltonian and imposed the constraints on it. Well, now that we know the trick, it's very easy. To go to Jacobian would be just this term minus this term. This term, the linear term will cancel out. So it's half x dot square minus half x minus y whole square. And if you now try to get rid of the x dots, all the x dots and y dots in terms of px and py, of course you wouldn't be able to because you can't get rid of y dot here. But you don't need to, because you don't have the y dot actually. You end up with half of ex minus y whole square minus half of x minus y whole square. Right? So the canonical Hamiltonian restricted to the space does not have these still undetermined velocities. So it looks like a good thing. But the next step that we also demonstrated there is that if you try to calculate the equations of motion from this H0 and just work the whole thing out using the canonical equations, you will not get back the correct equations of motion. Okay. So H0 at least has the advantage that it does not have the undetermined velocities, but the disadvantage, it does not really give you the correct equations. But that's also easily, you can easily see why. To see that, again let's go do the generic thing. Let's get rid of this example from the board, and so del H0 del q dot beta was 0. What about del H0 del qy? Q, all the positions. The canonical equation of motion would have been del H0 del qy is equal to what? Minus pi dot, right? Let's see whether we are going to get that. Well, this is our H0. Del del qy, the PAs of course are independent, so they are constants, but you of course have to differentiate this. Well, what about d beta q dot beta? Q dot betas don't depend on the q's. They actually are, you don't know any connection at all. That was the problem. But g betas, they depend on qi's, right? So del g beta del qi q dot beta. And what about the Lagrangian? Lagrangian of course has qi dependence, but in two places. Once in the q's, once in the f's. So minus del L del qi will have to be done, and I will have to replace the q dot a's by f's. So I'm not just writing that again, but you have to keep in mind that's what you're doing. And then in the f's, so del L del q dot a del fa del qi, right? Okay? But notice that here this term does cancel with this term, and this term is minus pi dot once you impose the equations of motion. But that's not the only thing you have. You also have this, right? So pi dot doesn't work out to be del H minus del H0 del qi. It would have if this term had not been there. Okay? It's actually this is on the right side already, so should have been plus, but what I'm going to do is change the g beta here. Remember, g beta is actually was part of the constraint. The constraint equation was phi beta is p beta minus g beta, which was a function of q and p. If you differentiate phi beta with respect to qi, the p beta part of course will contribute nothing. The g beta part will give you this del g minus del g beta del qi. So, this is minus q dot beta del phi beta del qi, right. So, this is what the thing changes to. It is not del minus del qi of the canonical Hamiltonian, there is an additional piece. Well, actually it does not stop there. This is for the position derivative. If you now did a momentum derivative, now which momenta can I differentiate with respect to? The ones which are independent, of course, not the p betas. But if I do this, so what is this going to be? Now have I lost the thing? No, it's still up there. So what is this going to be? Fa, right? Actually, when you differentiate that, you should change that to PBFB, right? That being a dummy variable. But when you differentiate, you get a delta AB times FB, so you get an FA. That's easy. But the thing doesn't end there. You have PB del FB del PA, right? Because the F's depend on the momenta as well. And in the G beta, so you get del G beta del PA q dot beta, a similar term to the one which survived there. And what about the Lagrangian? In the Lagrangian, do you have any momenta, the PAs at all? In the F's, right? So, that is going to be minus del L del q dot B del FB, again with that substitution, then FB del PA. Once again, it is not as bad as it looks, because this term and this term does cancel out, right? They are the same thing. But and if
Can you remind us what the FA was?
FAs were actually Q, the first RW Q dots. Lagrangian has Q and all the Q dots as argument. Other than the first RW Q dots could be replaced by the corresponding functions of Q's, P's and Q dot betas. Okay, so those were the FAs. So del H0 del PA, ultimately FA is by, of course, something we would have loved, just because this is Q dot A, right? Q dot A is del H0 del PA is what we would have loved to get. But we don't have that, we also have this term. So we end up with, this is one equation we end up with. We end up with Q dot A is del H0 del PA plus, well, it should have been a minus because I am moving it to the other side, but I am going to do the same thing again. Instead of G beta, I am going to put in phi beta. Well, again, the PA, remember the PB, G beta has a P beta, but P beta is independent of PA. It's only the minus G beta term which contributes. So this gives you Q dot beta del phi beta del PA. So you actually get to see something which is like the canonical equation, except that you have two additional pieces. And now you can actually make it even closer to the canonical equations simply by demanding this, that instead of your canonical Hamiltonian HC, you will define something called a total Hamiltonian, which is HC at gamma p by my H0, the Hamiltonian we started out with, plus, okay, plus now that might look like a problematic thing, because after all Q dot beta, okay, you don't know what Q dot beta is beforehand, but after you solve it, you are going to get Q dots, and those Q dots will not necessarily be constants. So putting in Q dots there may look like you are trying to treat that as a constant, right? However, note that when you differentiate this with respect to say Pi or say qi. Okay, this one. This additional piece, what will that give you? Q dot beta del phi beta del qi, right? It will also give you one more term, partial derivative of that q dot beta with respect to qi, something which I don't really have much of a handle about beforehand, times phi beta. Okay. But the great thing is, if after doing all these derivatives, you say now I am going to stay in my constraint space, what are the phi betas there? 0. So, what you cannot really write is this. You cannot say that del H0 del Qi, or let us write it from the other side, Pi dot. You cannot really write minus del Ht del Qi, right? But what you can write, and this is what we are going to do, and tomorrow we are going to use this a lot, this is so called weak equality. Weak equality by definition is equality on gamma p. Once you calculate everything, after that you impose the constraints. You don't impose the constraints beforehand, you do partial derivatives just the way you would. After doing all the calculations, if you impose the constraint, you are going to get Pi dot equals weakly equal to partial derivative of Ht with respect to Qi. Weakly equals means after you calculate it, you have to impose the constraints, not before. This is what trips up most people. You impose those constraints after you do the partial derivatives. Okay? So, you are not saying phi beta is always 0, so why do I do a partial derivative at all? You are not doing that. You are treating phi beta as a function, genuine function, doing all derivatives that you want. After that, after you have calculated, you are going to impose the constraint. Now, okay, q dots also, you could do exactly the same thing, right? But there is only one catch here. This is an equation only valid for the first RW q dots, not all of them, right? Because I could only do a partial derivative with respect to the independent PAs. However, suppose I just tried to use this and did a partial derivative with respect to those dependent P's, the P betas. Now, H0 we already know does not depend on the P betas, right? H0 has only Q's and PAs, right? We actually showed that it doesn't even have the Q dot betas, but it only has Q's and PAs. So, del H0 del P beta would be 0. And what about del phi beta del, so I should really then say, okay, let's try del H0 del P alpha. That's 0. And del phi beta del P alpha. Can anybody tell me how much that is? What was phi beta? Phi beta was P beta minus G beta Q PA. The G betas don't depend on the P betas at all, right? They depend only on Q and PAs. Yeah, that's a delta, not a 1, a delta alpha beta. So, this is delta alpha beta, and because this is delta alpha beta, this equation becomes trivially correct even for those later indices, right? For the first RW indices, this is a non-trivial result which comes out of a lot of calculation. From RW plus 1 to n, this is actually trivially true. And therefore, you can actually write this for all the A's, that is, this could be Q dot I is, it works for the A's, it also works for the alphas. Works for A's non-trivially and works for alphas just trivially. But that gives us the advantage that you don't need to write two sets of equations for the different kinds. You can just write this, and Q dot I is again weakly equal to plus del Ht del Pi. Okay? So, this weak equality thing is actually going to play a very important role in the next subsequent part of the theory. The subsequent part of the theory would essentially involve looking at these constraints that will come out. The problem will be do I get back, even if I start with HT, that is, start with HC, add a q dot beta phi beta with that. If I start there, do I get back all the Euler-Lagrange equations of motion? The answer is yes, but not necessarily directly, because the equations you may end up at the beginning will have primary constraints, but then these primary constraints will also have to stay true at all times. So their persistence, the time derivative being 0, may give rise to secondary constraints. Their persistence might give rise to tertiary constraints, and you may end up with a long list of constraints. Thankfully for finite systems, this always ends. But once you have got all these constraints in, you will find that all these constraints and the direct equations together will actually give you back Euler-Lagrange things. And okay, so yeah, I'm already out of time today, so I will not start on the next part. But next part, at least what I will do is I will at least show you this at work for some examples. Again, the same old examples that we have done with the Lagrangian case. Show how you will get the same equations of motion once you do this properly. That is, remember to use weak equality. And if I have, okay, I may not have time to go through the full Dirac formalism, but at least where the Dirac brackets come in from, we will try to indicate that. So I think that will be the agenda for tomorrow. Any questions for today's thing? Yeah.
So usually when one thinks about extremization problems, people like to think in terms of Lagrange. If you have an extremization problem and
With the
constraints, you think in terms of Lagrange multipliers, right?
In fact, actually, you will see that these q dot beta phi beta,
Those are the Lagrange.
well, basically you will replace the q dot betas by v betas.
Yeah.
Those will be your Lagrange multipliers, basically.
Okay, yeah.
And if you took this from the extremization for a point of view, with the Hamilton's version of the action principle, those would essentially play the role of Lagrange multipliers there. Notice that they have just the same form, right?
Yeah, that's what I.
Constraints times things. These are actually Lagrange multipliers. It will turn out that in some cases the Lagrange multipliers will be explicitly determined by the equations, not the equations themselves perhaps, but by their constraints and the consistency of the constraints. If your problem had, so there you have things called first, so unfortunately language is a bit of a problem here. We have primary constraints which you have at the beginning. Then you have constraints which come from that, secondary, tertiary and so on. So that's one classification. There's another classification of once you get all the constraints, you can classify them as first class as opposed to second class. If all your constraints happen to be second class, then these Lagrange multipliers will be determined by the equations themselves. If you end up with constraints which are not at least all second class, then the multipliers corresponding to those constraints, the ones which are first class, will not be determinable from the equation. They will stay undetermined, and they are basically what gives you rise to those gauge symmetries in this formalism. So presence of first class constraints essentially tell you that you have gauge symmetries. We have not really talked about what first class constraints are, but okay, everybody here is familiar with Poisson brackets, right? So we will not spend a lot of time describing Poisson brackets, but the Poisson bracket language will be useful to describe what are first class and second class constraints. That's what we are going to do tomorrow.
So these formats, like yesterday's class, we saw that there are two examples where one has a gauge symmetry, one doesn't have any. So this is true for both the.
What in the Hamiltonian also, that will come out through a different form. In particular, you will end up with, say, the Lagrange, our favorite example, which is no longer on the board right now. There you saw two examples, one with a plus sign and the other with a minus sign. One had a gauge symmetry, the other didn't. You will see the one which didn't have gauge symmetries are the ones where all the constraints are second class. So ultimately, all the Lagrange multipliers will be uniquely determined from the equations themselves, okay, which essentially means your solutions will be completely known. On the other hand, if you go back to the other case, the one where you did have a gauge symmetry, there will be two constraints there too, but those two will be first class. Okay. First class constraints essentially are constraints whose Poisson brackets among themselves vanish identically. So if you have a constraint whose Poisson bracket with every constraint vanishes, Every primary constraint vanishes, sorry, not every constraint necessarily. So you have this primary constraints which actually go into this HT, right, the q dot beta phi beta, the phi beta terms. If you have something whose Poisson brackets vanish with all the primary constraints, you call that a first class function. If that's a constraint, you call it a first class constraint. If all your constraints are first class, or even if you have some constraints which are first class, there will always remain some Lagrange multipliers which cannot be determined by the equations, and that will give rise to symmetry. You can then change them as you want and you will get different solutions. That essentially is the gauge symmetry kind of thing. The connection is actually pretty straightforward, although takes some length of time to get there. That is, the conclusions you draw from both formalisms are the same, the approaches are different.
So there is this thing called Rauthian, right? Which is
Yeah, Rauthian is where you sort of get, but that's really not the same thing. But there you don't get rid of all the q dots, you get rid of some of the q dots, keep some of the.
that's your choice.
That you did not have a singularity. The system was not singular.
Rauthian calculation is not a singularity, but if you have a singularity, can you use the Rauthian?
Essentially, you are using the Rauthian, but the Rauthian alone will not work. That's why you need these additional pieces. Essentially, the same thing. For non-singular systems, you tried doing this same approach with the Rauthian. It's essentially the same thing.
So, can you just repeat that statement? I mean, for constraints which commute with the primary, Poisson commute.
Poisson commute. Okay, that I think is best said tomorrow because I didn't. But let me just. You all know that Poisson brackets with the Hamiltonian is basically a way of finding out time dependence, right?
Yeah.
So basically, these equations can be written down essentially as Poisson brackets, right? Pi comma, and the only thing is here the Poisson brackets will have to be calculated first, and then you have to impose a constraint. That's what the weak equality is about, and this is also this Q I with HT, right? Now in your HT you have this H0 piece and you have this q dot beta phi beta piece. You can, okay, we will see later tomorrow that instead of H0 we can actually use any H which matches H0 on the constraint surface, right? If you don't use H0 itself but use some other function, when I say other function I mean it's a different function on the entire free space, but when you confine yourself to gamma p, it's the same thing. So the general HT that will be used is something like H plus V beta phi beta, where these V betas are the Lagrange multipliers. And basically, if this is your HT, then when you are taking, say, when you are trying to ask a question like, is a particular constraint itself going to persist? You will insist that phi alpha's Poisson bracket with HT has to be 0, right? But then you will end up with phi alpha's Poisson bracket with H plus V beta times phi alpha's Poisson bracket with Q, phi beta. Okay. So there, whether is this matrix of phi alpha phi beta Poisson brackets, if that's invertible, what you end up with is you can find out the V's directly. If that's not, then some of the V's can't be found out. That basically is behind this first class and second class qualification. Among the primary constraints, the ones which are first class will essentially give you a non-singular part of the matrix, so they will not, and they will essentially vanish in this equation. They will just drop off from this equation, so their corresponding V's can't be found out. The other V's can. Okay. So this distinction basically comes out automatically from the Poisson bracket, and then the other V's can be found out. So if you plug them back, so I'm just trying to give you the final answer here because I may not be able to get to that tomorrow. But if you just find out all the V's, which you can find out for those corresponding to the second class constraints, plug them back in the HTs, then you can show that Poisson bracket with the HT can be replaced by another kind of bracket where you take into account this additional piece for these V's automatically, and that is what the Dirac bracket really is. Okay, I will try to indicate how that works, even if I can't get to that fully.